I'm gonna go by Cannon Powder. This is my tutorial series on how to make video games with the Fuze app for Nintendo Switch. This initial tutorial is looping animations, and we'll be making a project in Fuze which demonstrates one type of these. Most of this video is focusing on the fundamentals of using Fuze. First, I'm going to explain what making a video game means with the Fuze app. Most games you can play on a Nintendo Switch are accessed through specific Nintendo Switch apps. These apps are what can appear on your home screen, and you can get them from physical game cartridges or the Nintendo eShop. For example, Smash Ultimate and Fuze both have Nintendo Switch apps, as you can run them from your home screen. The games you make with Fuze don't get their own apps. Instead, Fuze allows you to create a program file for each game, which is a document that you can write lines of code in. Each of these games can be played by opening its program file and then pressing the plus button on your Nintendo Switch to run the code inside of it. Let's start by making a program for our tutorial game. We do this by going here and creating a new project. In Fuze, a project is a folder used to represent the program file, and ties it to the title of the game, the name of the author, a description for the game, and a thumbnail. This should automatically open the program file for our tutorial game. You can try writing lines of code in this program file. This is a print function, which will make the text inside of the brackets appear on your screen. But if you run the code by pressing the plus button, nothing seems to happen apart from the autosave, which is triggered whenever an unsaved program stops running. Why? We're going to have to look at what a video and a video game are and how Fuze runs video game code. A video is a sequence of pre-made images that appear brief enough to make it look as if there's motion between them. A video game is a similar sequence of images. However, instead of being predetermined, the specific images are made in the moment based on the actions of the player. These images in videos and video games are called frames. When Fuze runs a program file, the code does four things. It can store information, it can design the frames that appear on your screen, it can read input, and it can perform processes which complement the video game. For example, playing audio. To organize when it does these four things, Fuze runs the code line by line as fast as possible, while also keeping track of time. Your Nintendo Switch has a limit for how fast frames can appear on your screen, which is 1/60th of a second, so our tutorial program file appears to do nothing, because while it designs a frame with the print function, the code finishes running before the game can stay on your screen. Now how do we fix this? It usually takes more than one line of code to design each frame. So to make designing frames easier, Fuze starts by assuming all of your code is for the same frame, and gives you a function you can write which tells it that all the code after is for the next one. This function is called update. When a game is being run, Fuze will try to run all of the code before the next update function within 1/60th of a second. Then, when it reaches the update function, it will wait until this time has passed. Once the 60th of a second passes, your screen will display the frame that was just designed, and Fuze will try to run all of the code before the next update function within another 1/60th of a second. If a code segment between update functions takes longer than 1/60th of a second to run, the next code segment will immediately start running when the update function is reached, and the frame will end up taking longer than 1/60th of a second to update. You can see an example of this happening here. Back to our tutorial program file. If we add the update function after the print function, you can see that running the file will make the contents of the print function appear in the top left of your screen for a brief moment. The more update functions we add, the longer the text in the top left of your screen will remain. Now, most video games don't automatically stop running after a certain amount of time. Usually, a game will run as long as you don't stop it yourself. For example, if Smash Ultimate always stopped working 15 minutes after opening, this would be a problem. And right now, that is exactly what happens with our tutorial program file. So how do we fix this? Just like how the code automatically runs as fast as possible until you use an update function to pace it, the code automatically runs line by line until you use a detachment. A detachment is a segment of code which can run in a different order relative to the rest of your program. For example, when the code is run line by line and reaches a detachment, the detachment could run multiple times or be skipped over. To make one, you need to write two lines of code called a detachment head and a detachment tail. Different types of detachment heads create different types of detachments, and need specific tails. The detachment is created between the head and the tail, with the head written before it and the tail after. For our tutorial program file, we can use a loop detachment. You write it with the loop detachment head and the repeat detachment tail. This kind of detachment will keep repeating running the lines inside of it until you stop running the program or use a break statement. Just to explain how a break statement works, when it's run inside of a loop, Fuze will stop running the code inside of the detachment. Skip to the line after the detachment tail and continue running the code from there. If it's used outside of a loop, a break statement will cause the program to immediately stop running. We don't want a break statement in our program file. What we do want to add inside of our loop detachment is an update function. This way, when we press the plus button, the program will run until we decide to stop it by pressing the button again. Now, Fuze runs video games by designing frames between update functions. So why does the text from our print function stay across all of our frames, even though the screen looks frozen? It's displaying close to 60 frames each second, but we only use the print function for our first frame. This is because Fuze keeps details designed on previous frames. If we move the print function inside of our loop, you can see that each frame, new text is added to what was already on the screen. Why does Fuze do this? While it tries to run code as fast as possible, if it takes too long to update a frame, the program will slow down, and some frames can have a lot of detail. Your Nintendo Switch screen has 921,600 pixels, and when plugged into a TV or other external screen, has to deal with 2,073,600. Each of these pixels can be one of 16,777,216 colors per frame. It would take Fuze way too long to update each frame if it has to consider every possible pixel combination each time. So instead, it uses tactics to save computing speed. These include having simpler functions which determine large numbers of pixels at once, like the print function, and adding to, instead of changing, details decided in previous frames. Of course, in many cases, it would be easier to remove details between frames. So Fuze provides the clear function. When this function is run, all details for the next frame that were decided earlier in the code, including details from previous frames, will be removed. If we write this clear function at the top of our loop, then when your tutorial program runs, it writes the text in the top left corner of your screen each frame, making it look frozen again. Now onto our project. For this first video, we're going to make a program that, when it runs, shows a spinning blue square move from the middle of the screen to the right and disappear. Then, when it's gone, reappears from the left side and repeats this pattern of moving from the left of the screen to the right indefinitely. To do this, start by removing your print statement. We're going to make the square in our program using another one of Fuze's visual functions, the create circle function. The create circle function allows us to design a basic shape, which we can then add to the next frame using the draw shape function. The specific purpose of this create circle function is to design circles of different sizes, and since you can't create a perfect circle with a grid of pixels, it creates shapes with so many flat sides they look like they're circles. This is useful because the function allows us to choose how many sides the shape we design has. We can use it to make pentagons or decagons, or in our project a square, but to use this function, we need to put 4 numbers inside of the brackets, which we can separate using commas. The first number is the horizontal position of the center of the shape. We want the shape to start in the middle of our screen, so we can use the gwidth function. This function gives us the number of pixels wide the screen is, and it changes depending on the horizontal pixel size of the screen your Switch uses. For example, the 921,600 pixels in your Nintendo Switch screen are organized in a grid. They're divided into 720 rows with 1,280 pixels each. So your screen is 1,280 pixels wide and 720 pixels tall. You can refer to different points in the grid using coordinates, with 0, 0 being the top left corner, and the dimensions of the grid, which are 1280 by 720 for your Nintendo Switch, being the bottom right corner. So if we write that the horizontal position of the center of our shape is half the width of the screen, it should be in the horizontal middle. The second number in the brackets is the vertical position of the center of the shape. For this, we can divide the g height function by 2. The third number is the radius of the shape, or half of the size of the shape if it was a circle. We don't need a specific number, so let's put 1/8 the width of the screen. The last number is the number of sides our shape should have, so we'll put 4 to make it a square. To use the draw shape function, we need to put our square inside of its brackets, so we're using a variable. Variables are words that don't mean anything in the Fuze language, but mean something to individual program files. Break is a statement. Loop is a detachment head. but some words don't have meanings in Fuze, like vehicle or brake with a 3 instead of an E, so individual program files can give these words their own meanings. The word square means nothing to Fuze, so we're creating a new shape with the create circle function and defining square as that shape. This way, when we use the draw shape function and put the word square in its brackets, we're telling the function to draw the shape we made earlier. And if you run the program file, you'll see the square appears on screen. To turn our square blue, we'll use the set shape color function between the create circle function and the draw shape function. This set shape color function needs two things in its brackets: the shape it's coloring and the color it's using. In Fuze, colors are represented by a combination of 4 numbers inside of curly brackets. Each number can be as low as 0 and as high as 1. If it's any lower, Fuze treats it as 0, and if it's any higher, Fuze treats it as 1. Every color your screen can make is a combination of red, green, and blue, so the 4 numbers represent red, green, blue, and opaqueness. Our square is, by default, white, and not see-through at all, so its color value is 1111. We want our square to be blue, so let's make its color 0.211. Testing this shows that it worked. Now we're going to get our square to rotate. We can write the rotate shape function, which takes the shape to rotate and the degrees to rotate it by. Since we made a square, a 90-degree rotation will look the same, but let's start with a 45-degree rotation. This way, when we run our tutorial program, the square will start out straight. To get our square to spin between frames, we'll need to change its rotation amount to a variable, which can be adjusted by the code over time. We'll create a variable for its horizontal position as well, because this will also need to be adjustable. I'm calling these sqpose for the horizontal position and sqrtn for the rotation. If we give them their default values, then even though they can be adjusted over time, whenever the program starts, the square will be straight in the center of the screen. Now that we have the variable for rotation, we'll change its amount by 3 degrees between each frame. You can change the speed of rotation by replacing the 3 with a number of your choosing. 5 is noticeably faster, and 2 is noticeably slower, but there is one problem. The longer the program runs, the higher the rotation amount becomes. The larger a variable, the more information the program has to remember. Even if this is very minor, it's not sustainable for our program, because your switch has a limit to how much information it can store. So, we'll use modular arithmetic to reset the rotation variable every 90 degrees. Since our shape is a square, the illusion of it spinning still works. Finally, we'll make our square move off screen. First by having it move 1/80th of the width of the screen per frame. Next, we can use another modulus to move the square to the left of the screen whenever it gets too far to the right. Now, we're not going to make this modulus the width of the screen, because if we did, the square would teleport while half of it's still visible. So to get our modulus, we'll take the width of the screen and add 1/4 the width of the screen multiplied by the square root of 2. Why? We want the illusion of the square disappearing from the right side of the screen, moving to the left of the screen, and then entering from there. This means there has to be a short amount of time where the screen is completely empty each repetition. The radius of our shape, if it was a circle, would be 1/8 the width of the screen, and its diameter would be double, or 1/4, which means, since it's a square, its diagonal length is 1/4 the width of the screen as well. But if we just added this to the width of the screen for our modulus, then if the square ever exits the screen while being perfectly diagonal, it will instantly enter from the other direction without enough time for the illusion to work well. So we need a higher value. One good number we could use is the diagonal length of a square with a side length equal to the diagonal length of our square. Using the Pythagorean theorem, we can determine this length to be the diagonal length of our square multiplied by the square root of 2. The last thing we have to do is make it so our square doesn't partially appear on screen whenever it teleports to the left. So going back to the create circle function, we subtract half of the value we just got from the position variable of our square. Now our first program is done. We have a looping animation of a rotating square which appears from the left side of our screen and disappears to the right. If you want, you can try adjusting different values. For example, if you use a variable for one of the color values, the loop square will change color as it moves. You could make it look like it's pulsating by doing this for its opaqueness, or even reverse that value. But remember that if you remove the clear function, the squares designed in previous frames won't be cleared, and clutter the screen instead.